All right, hey everyone. So this is our last week of organic chemistry, and sad day, but we've got a few examples that we're going to go through here. And the first example that we're going to be talking about is having to do with combustion. Now we know combustion is when a fuel reacts with oxygen to produce carbon dioxide or water. You know, the main part of this unit is in unit A, we did that. And in unit C, now we know how to name and draw organic molecules. So they can give us really any organic molecule. We have the capacity to name and draw it. And then we just do the same thing that we did in unit A. So if I look in this example, it says 2-ethyl 1,3-dimethylbenzene has a delta FH equal to negative 80.1 kilojoules per mole. Now, when I see delta FH, I'm immediately thinking, ding, 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 Hess's law 2.0, okay? It says write a balanced thermochemical equation for the combustion of that chemical, and then use it to calculate heat released. So I have to think, okay, balanced thermochemical equation is a balanced equation with delta H on the end. How can I find delta H? Well, I can use Hess's law 2.0, which makes sense because they gave me delta FH. So the first thing I need to do is identify what this chemical looks like. So they give me, I'm just going to write it down. They give me 2-ethyl 1,3-dimethylbenzene. Okay. So the first thing that I have to do is draw this chemical, all right? So if I look at this, benzene is my root. So I'm going to start with a benzene right here. Circle in the middle. Okay. And then I've got 2-ethyl and then 1,3-dimethyl. So the 2-ethyl is on carbon 2, 1,3-dimethyl. Di means 2. It means there are 2 methyls. They are on carbons 1 and 3. So I got a methyl here and a methyl here. And then I've got an ethyl on 2 that looks like this. Perfect. Now, if I was going to write a balanced thermochemical equation or balanced equation, I don't want to use this. I need to condense this into an empirical formula, which only has carbons, hydrogens, oxygens, whatever. Basically the molecular formula. So what I need to do is I need to count how many carbons there are, how many hydrogens there are, and use that. So if I look at this, I've got 1, 2, 3, 4, 5, 6, 6 from benzene, 7, 8, 9, 10. 10 carbons. So I'm going to write C10. Now hydrogens is tricky. I've got 3, 6, 9, 10, 11. And then I have to remember that benzene has a hydrogen on every single carbon. However, if I now have groups here, I cannot have a hydrogen here as well, because that would mean that the carbon has 5 bonds. 1, 2, 3, 4, 5. So these hydrogens here, here, and here do not exist, only here, okay? So I got 3, 6, 9, 10, 11, 12, 13, 14, H14. We don't really know if this is it's not a solid, okay? Most benzenes are liquids, okay? But at this point, it's not really gonna matter, okay? I don't know why I erased that. Just gonna erase the hydrogens. Okay, we have our molecule. Now, if I was going to write combustion, I have to react this with oxygen. And the products are going to be CO2 and H2O. This is just simple combustion, so water vapor. Now, if I was going to do a thermochemical equation, at the very end right here, I'm running out of space, I'm going to do it up here. I have to have a delta H, which is in kilojoules, okay? So for this reaction, if I want to write a thermochemical equation, I need to find delta H. Now, how do I find delta H? To find delta H, I have to use Hess's law 2.0. Delta H is equal to the sum of N times delta FH of my products minus the sum of N times delta FH of your reactants. Okay, remember we use Hess's law 2.0 to basically find delta H when we have no information, which we don't really hear. Now, before I can use this, we see that there's n's here. Those n's come from the coefficients of my equation. So before I can use Hess's law 2.0, I need to balance this equation. Okay, you guys all know how to balance. We use inspection first. 10 carbons here, put a 10 here. 14 hydrogens, so put a 7 there. 7 oxygens plus 20 oxygens is 27. So here I'm going to put 27 over 2. Okay? And now I'm going to do Hess's law 2.0. Okay? So Hess's law 2.0 says we need to first start with the products. So products are carbon dioxide. So N for carbon dioxide is 10 moles. And I'm just going to use square brackets here. And the delta FH for CO2 is negative 393.5 kilojoules per mole. How do I know that? It's in your data booklet. Plus 7 moles times negative, I think it's 241.8 for water vapor. Let me just check my data booklets. Yep, negative 241.8 kilojoules per mole. Okay, and then I have to subtract reactants. Now, what we remember is that delta FH for an element, so water, sorry, not water, oxygen, right here is 0. So all I have to include is the fuel term. Now, what is that fuel term? In the question, I believe it was negative 80.1. So there's a 1 there. 1 times negative 80.1 kilojoules per mole plus 0, but I don't need to write that for this. Okay? So all I'm going to do is solve this equation with my calculator. So I'm going to do 10 times that. So 10 times negative 393.5 plus 7 times negative 241.8 is negative 5,627.6. Negative 5,627.6 kilojoules because the moles cancel out. Plus 80.1 because negative and a negative makes a positive. So my delta H for this reaction with a coefficient of 1 is negative 5,547.5 kilojoules. Okay. So what I'm going to do is I'm going to take this number and I'm going to put it up here. Negative, if you want to use sig digs, that's fine. I'm not for this example. 5,547.5. Okay, kilojoules. Okay, that's delta H. Okay, take a look at that. So again, how did we get to that point? We found the molecular formula for our chemical, wrote a balanced thermochemical equation, okay? Used Hess's law to find delta H and subbed it up there. Now, the question is not done. The question then says, I'm going to erase this. The question then said, how much energy was released for, I believe it was 100 grams of this fuel, okay? So now I'm looking for delta H again, but we already have delta H. So this is confusing. But remember, this delta H is for 1 mole. 100 grams is not 1 mole. So I need to find the new delta H. How do I do that? I remember that there's a formula. Delta H is equal to N times delta RH. Okay? Now, N comes from mass over molar mass, which is 100 grams divided by the molar mass of this. So to find the molar mass of that, take 10, multiply by 12.01, add 1.01 times 14, and I get 134.24 grams per mole. Do 100 divided by that, and I get 0.001 7,449 ... Okay, that's N. Well, now I need to find delta RH. Okay, this is where a lot of people get confused. They're like, oh, delta RH is negative 80.1 kilojoules per mole. That's wrong. That's not delta RH. That's delta FH. R stands for reaction. What type of reaction is this? It's combustion. So I have to find delta RH for this reaction. How do I do that? I kind of jig this formula around and say delta RH is equal to delta H over N. Okay, it seems a little weird, but remember that delta RH doesn't change. It's the same for every reaction. So you have to say to yourself, do I have a delta H? Yeah, I do. Do I have an N for this? Yeah, I do. So all I'm going to do is negative 5,547.5 kilojoules divided by 1 mole is going to give me negative 5,547.5 kilojoules per mole. And then all I'm going to do is multiply those numbers to figure out how much energy was released times negative 5,547.5. And I'm going to get negative 4,132.52 ... kilojoules. And if we use 3 sig digs for our final answer, negative 4.13 times 10 to the power of 123 kilojoules. Okay. So again, you know, we're making some connections to unit A. Okay. The biggest thing is that you can look at this. The biggest thing that you need to take away from this unit is I can look at this formula, this chemical. I can write a molecular formula after I draw it. Okay. Then I can balance this, find delta H using Hess's law 2.0. But the biggest thing is from this unit, the only thing that we're adding is we're drawing this. That's it. Everything else, guys, is from unit A. So we have to jog our memories a little bit. Hopefully this helped.